Hello, I'm Chano. I'm going to introduce our work, Video-Based Person Re-Identification with Spatial and Temporal Memory Networks. Video-based person re-identification aims at retrieving a person of interest from a set of pedestrian videos. Video frames provide rich information to specify a particular person, but they often contain spatial, temporal distractors. Spatial distractors, for example, include playfields, streetlights, or concrete pavers in the background, while temporal distractors include such as a person of interest disappear at the end of a video. Our motivation is that the same spatial distractors repeatedly appear in video sequences, as they are captured by a stationary camera. Also, we can observe that there are several prototypical patterns among temporal distractors, where such patterns can produce crucial keys to predict which video frames we have to focus on. Based on the motivation, we propose to leverage two external memories, called spatial and temporal memories. During training, we train the spatial memory to save features of spatial distractors, while temporal memories are trained to discover prototypical temporal patterns and to memorize corresponding temporal attentions. We then use these memories as a lookup table during evaluation, and ease the difficulty of handling the challenges of video-based RE-ID. We now provide a brief overview. Our model takes a video sequence. Each video frame is processed by an encoder to produce two query maps for the spatial and temporal memory, and a single person representation. Our model accesses the spatial memory using the corresponding query map. Using the output of the spatial memory, we refine the original person representation not to contain features for scene details. We repeat this process for each frame independently, obtaining frame-level refined person representations. We then access the temporal memory, using the corresponding query maps. The temporal memory provides a temporal attention, which indicates the importance of each frame. Using this attention, we temporally fuse frame-level person representations, resulting in a single person representation. We train our model with the combination of identity classification loss and triplet loss. Motivated by a deep supervision technique, we also impose the loss on the frame-level person representations where temporal average pooling is used instead of the temporal memory. We now describe our memories in detail. We address the spatial memory using each d-dimension feature of the query map. We compute matching probabilities between the query feature and keys of the memory by cosine similarity, and normalize the similarities. We then compute the weighted average of memory values based on the probabilities. The result is subtracted from the original person representation to suppress information for distracting scene details. The temporal memory operates similarly as the spatial memory. We first encode the temporal context of the input sequence using an LSTM module, and the output is used to compute the matching probabilities. Based on the probabilities, we aggregate memory values, where the aggregated value is used for a temporal attention. We empirically found that our model keeps addressing particular keys only. This is because we do not have any supervisory signal that can tell which key should be matched to the input query. To address this problem, we impose the minimum and maximum values of the probabilities of a certain key should differ by at least a pre-defined margin. We combine this loss with the identification loss for the final objective function. Now we provide experimental results. To show how our model accesses the spatial memory, we retrieve frames whose query features show high matching probabilities with a certain key. As a result, we can retrieve frames that share similar distracting scene details, indicating that our model addresses the memory according to the scene details in each frame. We do the same thing with the temporal memory. We then observe that sequences that show similar patterns are retrieved using each key. When we see the trained temporal attentions below, they are activating discriminative frames without temporal distractors. We show the effect of the refinement by the spatial memory, showing the magnitude difference of person representation before and after the refinement. We can see that the differences mainly occur from scene details, implying our memory suppresses information for such details. We now show examples of generated attentions by the temporal memory. The results show that our temporal memory operates robustly against temporal distractors, highlighting informative frames. Though we input the same video frames but with different orders, the memory focus on the frames that show a person of interest. We found that previous methods compare their performance under different test strategies. We group those methods into two different groups for a fair comparison. We achieve state-of-the-art performance on both settings. Thanks for watching.